everyone. I am Saniya Koller, and in this video, I want to talk about an application in coronary heart disease. How do you interpret having a probability threshold of 25% when it comes to decision curve analysis? So basically, if your probability threshold is 25%, what does it mean? So I have another video that I prepared in the decision curve analysis playlist that talks about the probability threshold more. So please do see it. And please do subscribe to my channel for more updates as I continue building out more videos on decision curve analysis, which is very important. But here we're going to talk about you have a probability of threshold of 25%. What does it mean in terms of how you value false negatives and false positives, especially in decision curve analysis? Please note that here, this is just an illustrative example for a specific probability threshold, 25%. We could have chosen any one between 0 and 1. So I've just chosen 25% for an example. Hope you can understand the concepts because the analysis for any probability threshold, it'll just be extrapolating what you will learn in this video here. And this is just an example of a predictive machine learning model for coronary heart disease. And that's what decision curve analysis is really useful for, as I've shown in other videos, for helping us interpret the clinical net benefit and optimal values for a given predictive model. So that's what this threshold is 25% here. And this is just an example that we could use of a predictive model. And this is just an example of a probability threshold. So I just hope that this will be helpful, but this is just for a concrete example. And in reality, you would interpret it as needed for your predictive model, for your probability threshold. I'm going to give you a little overview of what is to come, a little bit of a review, but more detailed in terms of probability threshold of 25%. I want you guys to understand that example, but I want to walk through and go over what this means exactly. So again, please do subscribe to my YouTube channel for more videos on decision curve analysis, probability thresholds, and even more. So I have a lot of content out there, but in this video, I want to give you a detailed example, and I will be having other videos where I talk about other probability thresholds and how to interpret them. But here I want to talk about in a little bit more detail from start to finish on just one threshold and what it means. So I'll be giving a background on coronary heart disease because that's our application here, the disease of focus. I'll give a little review on predictive machine learning models like logistic regression, how those typically use a probability threshold of 50% for assigning predicted classes. Usually, if your predicted probability is greater than 50%, you are assigned to one class, a class 1, typically having the disease. And if your predicted probability is less than 50%, you are typically assigned to class 0, predicted to be negative, not have the disease. I'll also talk about and review false negatives and false positive mistakes here, and what those mean in the context of coronary heart disease. I'll explain probability thresholds. I also have a more detailed video on that on my channel. Please do see, and also in the bio below, I've included helpful links for you guys. But how probability thresholds can tell us the relative importance of false negatives to false positives, and how we can then apply, then the rest is sort of looking at 25% probability threshold, see how that is applied in a logistic regression model, and how false negatives are therefore worse than false positives based on the threshold of 25%. And just a very specific example. And then I'll go through confusion matrices for machine learning model evaluation, focusing on this threshold of 25%. I'll talk about how probability thresholds are used in the decision curve analysis net benefit formula. In particular, a probability threshold is PT, and how PT over 1 minus PT is a ratio used to calculate net benefit of different predictive models or decisions. But I have more detailed videos on that, but I will just show the role of it in the net benefit formula. And then how we can understand that probability threshold of 25% in terms of false negative and false positive errors. And ultimately, you'll see how one false negative is the same or worse than 3 false positives based on this probability threshold value of 25%. I kind of have given a spoiler alert, But because we can see that false negatives are worse than false positives, then one false negative is the same as or worse than three false positives based on that probability threshold essentially of PT equals 25% here. So yeah, please stay tuned in this video, but I want to give you just the overall structure and agenda, and please go to the parts that you need help with while bearing in mind that this is the overview for what I plan to cover in this video, and there are lots more videos on this topic on my channel. So again, please do subscribe, and please reach out with any questions along the way. In fact, coronary heart disease, CHD, is a type of heart disease which is when the arteries of the heart cannot deliver enough oxygen-rich blood to the heart. Because you can see here, this is a normal artery of the heart, and then this is an artery of the heart that has some plaques. So there's abnormal blood flow, which is very sad here. So a normal artery, there's no blockages, blood cells can flow through. And in coronary artery disease, there are plaques, by cholesterol and other things, the plaques, and blood cannot flow through. And there's not enough oxygen-rich blood that goes on those platelets. Oxygen-rich blood goes on the platelets through these blood vessels, which is very sad. So, in fact, CHD is the leading cause of death in the United States. So it is a very sad situation and serious. So in this video and this example here, there's so many variations inherently that can take place. But we are choosing coronary heart disease, but there could be different diseases or conditions. I even have a video on how decision curve analysis could be applied in non-clinical settings, such as like advertising fraud, for instance. So do check out my playlist again and subscribe for more updates. So there could be different diseases or conditions. So I've just chosen coronary heart disease, and when you have different diseases and conditions, interpretations can differ, and side effects and treatment versus not treatment, all of that can really change. We can also use different machine learning models. Here I wasn't too specific, but I did start off showing a logistic regression model, that S shape for predictions. But we can have many different types of machine learning models, like predictive models. We can have different probability thresholds and preferences. So here I sort of fixed it at 25%. I do have another video coming up where I vary various probability thresholds and show you how the interpretations will change for that. But there's so many variations, and this is just meant to guide and cement some concepts for you guys on what a probability threshold is in a specific disease condition, while reminding you a bit about machine learning models. So Yangshi, I just want to give us a quick recap of what we discussed in previous videos as sort of a foundation. So guys, please do check out my previous videos which go in more depth on these concepts, but I just kind of want to revisit and recap what we have discussed in those videos. So predictive models for like coronary heart disease, they can be of many different forms. So here I'm just going to show an example where we're going to look at logistic regression models and just see, for instance, that we have a model and we're trying to predict coronary heart disease, just basically heart disease from this model. We have this predictive model and we're trying to just predict this outcome from that data using that model and applying it on new individuals. So here, for instance, we have a logistic regression model predicting probability that someone has heart disease, as I was mentioning. So you have all these individuals here, and you sort of measure using logistic regression what's the probability that the person will have heart disease. And there's a saying that, and I strongly believe, and we all should believe, that all people are created equal. However, not all errors are created equal. False positive errors may not necessarily be the same as false negative errors. Wrong diagnoses can have various effects. A false negative, a FN, is falsely predicting that a positive patient is negative. So basically, in the false negative situation, wrongly predicting that a sick patient, a patient who has CHD, does not have it. And behind the scenes there is damage going on and treatment that SpongeBob was missing out on, potentially life-saving. It's also a false positive though, and it really depends on how you value things. So a false positive in FP is falsely predicting that a negative patient is positive. So the prediction is positive, but the actual truth is that the patient is negative for the disease. So here the doctor is very sad, and the machine learning model as well. And they're saying, I'm afraid to predict that ye have coronary heart disease. So it's like the doctor is sitting the patient down saying, I'm afraid this doesn't look good. And the patient looks worried. We don't know the actual truth in this situation. The doctor is predicting that the patient has coronary heart disease, but actually, in this case, like let's say the patient is Squidward. Squidward is full of life and love and actually was healthy and did not need treatment for coronary heart disease. And the impact of this false positive is that Squidward is now going through unnecessary and risky treatment for coronary heart disease. So you're sending a healthy patient for unnecessary treatment. We talked about probability thresholds and false positive versus false negative mistakes. If a probability threshold is 50%, then false negative and false positive mistakes have the same impact and both are equally bad. So you just want to minimize both mistakes. But if your probability threshold is less than 50%, so if your probability threshold is anywhere in this region, false negative is a worse mistake than a false positive mistake, basically. And if instead your probability threshold is greater than 50%, then you believe that false positives instead are worse mistake than false negative mistakes. Our probability threshold here at 25%. What we are saying is that a false negative mistake is worse than a false positive mistake. So please remember that this is sort of like background about how we can figure this out just looking at a threshold. And the default is 50%, but here we're seeing that we can vary probability thresholds. So here in our situation, a false negative is a worse mistake than a false positive mistake. Go in and I talk about all of this in my previous videos, so please do check those out. So I hope that those videos will be helpful for you guys, but we're going to be building on that here and talking about, in particular, the probability threshold of 25%, knowing that this means that we're more scared of making a false negative mistake than we are of making a false positive mistake. For coronary heart disease, it's like who wins a tug of war for this? They're saying, please go for treatment for coronary heart disease, CHD, and then they win if the predicted probability of being positive for a patient is greater than or equal to the threshold, PT. Otherwise, if the predicted probability that a patient is positive is less than the threshold, then you don't go for treatment. And in this example, like what if this is 25%? Then they say that you go for treatment, please, if the predicted probability of you being positive, of you having coronary heart disease is 25% or above, which seems like a lot when you think of this whole range of intervals from 0 to 1. Otherwise, they're saying, please do not go for treatment if the predicted probability you have of being positive of having coronary heart disease is less than 25%. So it's a tug of war, and who wins, given your predicted probability of having coronary heart disease, who wins? It's all based on what your threshold probability is. And in this example, we talk like, what if it is 25%? So how do you interpret that? If the probability threshold is 25%, like it is in this example, so that's between 0% and 50%, but does not include 50%. So basically, as we just discussed, since the probability threshold is less than 50%, then that just means that there are a greater range of probabilities where we predict positive for the individuals. So the probability threshold is 25%. Then basically we are predicting that the patient is negative, does not have CHD. If they have a predicted probability of CHD, that is less than 25%, less than this threshold probability, then we predict negative, which is just this interval here from 0 to 0.25. But we predict positive, that the patient has CHD, coronary heart disease, if they have a predicted probability for CHD that is greater than or equal to this probability threshold of 25%. So then we're predicting positive for this larger interval from 0.25 all the way up to 1. So this is the range for negative is here from 0 all the way, but not including 25% here. We predict negative for these individuals here. For just these people here, we're predicting negative for this. And for the others, we're predicting positive. We are predicting positive if their probability threshold is greater than or equal to 25%. The negative range is much smaller than the positive. So there's a greater range of probabilities where we predict positive for the patient. So if the patient has a predicted probability of 30% or 40 or 41% or anything greater than or equal to 25%, we basically are predicting that they're positive, that they have coronary heart disease. Whereas if they have a predicted probability that from the machine learning model of having CHD that is less than 25%, we are predicting negative, but there's more probability of us kind of predicting positive. So more ranges of predicted probabilities that are going to result in positive than in negative. So there's a greater range of probabilities where we predict positive outcomes, like of having CHD, than predicting negative. And what this basically means again is because it is a little bit likelier, we have more probabilities predicting positive than negative, it means that we would rather predict more false positives, like more times would we want to predict someone is positive, even if it's false, than predict that the patient is negative. Because negative, according to this viewpoint, when the probability threshold is less than 50% here, when it's less than this 50%, it means that we believe that wrongly predicting that someone is negative when they're positive, a false negative, is worse mistake than a false positive, than predicting that somebody who doesn't have CHD has CHD. So we want to focus more on reducing false negatives. So we are decreasing that probability threshold from 50% down here. 50% the equal errors. False negative is false positive, but since we are reducing the threshold, we are making the range where we say somebody is positive, we are making it even like 25%, 26%, anything. So we are increasing the chances of predicting positive than a negative. So because the threshold probability is 25%, there's more possibility of us predicting positive for individuals rather than negative. And that's because predicting positive, even if we do that, it's not as bad as falsely predicting negative. Because if we predict negative, it can result in a false negative or a true negative. And this could result in a false, so like this one could lead to either like a false negative or it could be a true negative. But this predict positive would lead to either a true positive if it's correct or a false positive. So when we do it this way, what's happening is that we could, if this is a false prediction, it would just increase the false positives we are making. But if it's true, then it's a true positive. Whereas here, if we predict negative and that's wrong, we have false negatives. And if it's correct prediction of negative, then that's a true negative. But we are trying to reduce the chances of having false negatives, even at the risk of increasing the false positives. Because for us, false positives are not as bad as false negatives because our threshold is less than 50%. So we'll notice here that we don't want to wrongly predict someone with CHD doesn't have it. That's a worse mistake in this situation than falsely sending somebody who's healthy for treatment for CHD when they don't need it. Based on the logistic regression model again, so it's a model based on any variables, like let's say again in this example that these are cholesterol levels, and the machine learning model could be anything. It can include as many different predictive variables as needed, but let's say that it is based on cholesterol levels, then the probability that we predict that the patient has CHD, the predicted probability that we have, is going to be equal to, based on the logistic regression model, it's going to be, the logistic regression model is going to be this model here, which is just 1 over 1 plus e to the minus beta 0 minus beta 1 times cholesterol level for the patient, which is the x-axis here, if we just have this one variable. And during the training, machine learning training, when we're building the model, this curve here, logistic regression model, the model will learn the specific values for beta 0 and beta 1 that are good estimates. It's trying to estimate the best values based on our data. But basically, if we use this model, as I was showing before, and these are patients who don't have heart disease in green and patients with heart disease, CHD, are in red, then if we instead reduce our probability threshold to 25% for the same machine learning model that this little guy, robot Pug, has learned, what we're essentially saying is that we plug in a patient cholesterol level here into our model and generate some predicted probability between 0 and 1. And if the probability that the patient has heart disease is greater than or equal to 25%, we predict that the patient will have CHD if it's greater than or equal to our probability threshold of 25%. All of these predicted probabilities, if we put it and the patients, based on the cholesterol level, we map it to this S curve, this logistic regression model. And if the predicted probability is above, greater than or equal to 25% based on our threshold, we'll say that the patient has CHD. That's what the little robot Pug will predict. Otherwise, we're going to predict if the patient probability is less than of CHD for the patient. If it's less than 25%, we will predict no CHD, that the patient has a healthy heart. And so again, this shows how the probability thresholds are useful, but you see that the range of probabilities where we predict CHD, where we predict the positive outcome, the positive class, this is negative, that the range of probabilities for positive are much more, this is a much bigger arrow than the range of negative, and it's because we rather give more positive predictions out there, even if there are more false positives as well, because we don't want to have, we want to limit as many negatives that we have. We want to make it stricter, because for us, identifying these weak hearts is more important. Minimizing false negatives is more important. So that's what this threshold will mean, but I'm going to show how we can quantify how much more we value and are scared of making false negatives over false positives in this video. So the way that it works is that we can collect information on like patient Pucci, for example, from surgeons and nurses, the doctors, etc. We can collect this information on Pucci, and then on the patient health information, various variables that we could need, like blood pressure, age, body mass index, cholesterol levels, various features that we can collect information on for a patient Pucci in this application here on patient data, demographics, all these things, family history, all of this, and we put it into a machine learning model that we have trained. And I have in other videos, and I will be talking about how we can come up with machine learning models for various predictive tasks such as coronary heart disease. But we put in this data of Pucci into a machine learning model that makes a prediction about Pucci's risk of having coronary heart disease, CHD. So then this machine learning model, which we have trained before, and again, I'll talk in other videos on this. The machine learning model takes Pucci's data and says, "Hi Pucci, please note that you have a 16% predicted probability of having coronary heart disease." So based on this, the doctor can then decide, based on this probability threshold, whether to predict if Pucci should go for treatment, to get well, and treated for coronary heart disease, or which is the bad outcome, or if Pucci should, just stay healthy, keep it up. So the doctor or Pucci or loved ones could decide whether this probability of 16% is high enough for, going for treatment versus not going for treatment. So here in this example, the doctor's probability threshold is 25%. Basically, the doctor is going to predict somebody like Pucci has coronary heart disease if the probability that they're predicted with is greater than or equal to 25%. And I have another video talking just about probability thresholds. So here for Pucci, because 16% is less than 25%, then the doctor will then predict, as I said, since 16% is less than 25%, the predicted probability that Pucci has coronary heart disease, CHD, 16% is less than the probability threshold of the doctor, which is 25%. So the doctor is saying that if you have a predicted probability of having CHD that is 25% or higher, I'm going to believe that you have coronary heart disease, and I'm going to then send you for treatment for coronary heart disease, essentially. So that's what the doctor is saying. I have this threshold probability of 25%. So if your risk of having it, your predicted probability by the robot, by the machine learning model based on your data, if that is 25% or higher, I'm going to, the chances of you having coronary heart disease, I'm going to send you for treatment. But since Pucci luckily has a risk of coronary heart disease at 16%, and 16% is less than 25%, which is the doctor's personal probability threshold in this case. Remember, probability threshold can be a number between 0 and 1. It's just a probability that is selected. Then the doctor says that since your predicted probability of coronary heart disease, since this value here, this value, it's less than my probability threshold of 25%. Since you have less than a 25% chance of coronary heart disease, I'm going to predict that you are negative, that you do not have CHD. So no treatment would be needed for you for coronary heart disease. So the doctor is thinking that Pucci is hopefully healthy because the 16% predicted probability of coronary heart disease seems to be not higher than the 25% threshold. So the doctor says your risk is still not so high, thankfully, touch wood. So I predict you do not have coronary heart disease, so you don't need any treatment. So out of the treatment versus no treatment, doctor says no treatment. So Pucci is predicted as negative and healthy, and thus is not treated for coronary heart disease based on this doctor's probability threshold of 25%. So now there are 4 possible outcomes. So we don't know the truth just yet. We don't know if Pucci actually has coronary heart disease or not, right? So we don't really know. But there's a confusion matrix that can help us figure out just how confused our model is and our predictions are. So we make these predictions given a probability threshold. So here in this situation, the probability threshold that we were using is 25%. And I'm going to show how we interpret that. But the idea is that we have these 2 types of accurate ones here. The true positive, the true negative, and then we have mistakes, false positives and false negatives. So basically a true positive, so these are the actual true conditions that for us right now, as we think of it, these are unknown, but at some point we're going to probably find out what the truth was of the matter, like what Pucci actually had in this situation, or any patient. So the actually positive means that the patient sadly had coronary heart disease. That's what this is saying. So when they're actually positive, they have coronary heart disease. Or they could be actually negative when they are healthy and they don't have coronary heart disease, which would be the ideal, that they're healthy, they don't have coronary heart disease. But our predictive model makes predictions. It either predicts your positive or it predicts your negative. So based on the probability threshold here of 25%, the model is predicting whether, based on Pucci had a predicted probability of 16%, which was less than 25. So Pucci was predicted as being negative. So Pucci was right here in this group, for instance. The patient Pucci was right in this group, predicted negative. So patient will not go for CHD treatment. So Pucci's predicted probability of 16% was less than 25%. That this predicted probability of 16% was less than the 25% threshold. Remember, this is the 25%. This is the doctor's threshold. It could be anything between 0 and 1. Anything between 0 and 1. So the false negative would be the worst case for Pucci, who's predicted negative here. So basically, the doctor, based on the predictive model, on the machine learning model, and on his, her, or their threshold probability of 25%, the model basically said 16% risk of coronary heart disease. The doctor said that the doctor's personal probability threshold was 25%. So basically, patient's predicted probability is less than the threshold, the doctor predicts negative. And if the patient's predicted probability of coronary heart disease is greater than or equal to the threshold, then the doctor predicts the patient is positive and needs to go for CHD treatment. So since 16% is less than 25%, the doctor says that Pucci should not go for CHD treatment because Pucci is predicted as negative. And in the false negative situation, so since Pucci was predicted as being negative, but that was actually false. Pucci actually has CHD. So the predictive model and the threshold here incorrectly predicts that a coronary heart disease patient does not have CHD. Basically, the model and the threshold here basically predicted incorrectly that Pucci did not have coronary heart disease, but Pucci actually had it. So we just have to look at the row and the column, and that's what each cell tells us. But on the good side would be instead that if, like, what we really, really want, I think the best case, especially in this situation, nobody wants coronary heart disease. So if the true negative is that, the model predicted that Pucci is negative, does not have CHD, and should not go for treatment, and in reality, Pucci actually doesn't have CHD, and it's good. Pucci skipped out on unnecessary CHD treatment, which is good. So the model correctly predicts that a healthy patient does not have coronary heart disease. So that's awesome. So that's great. Pucci saved money on future tests and stress, and saved stress and time and life and energy and side effects from treatment and all of that stress for nothing, if this is the case. But in the false negative, if Pucci actually has CHD and was not receiving treatment, then this would be really bad because, maybe CHD got lots worse. God forbid, but let's say that it could get a lot worse, and if this was detected earlier, maybe something could have been done, so this would be bad because maybe the CHD heart disease progresses, and it could have been better if it was detected earlier, but instead, since we thought Pucci did not have CHD, we didn't act on time and it got too late. So that could be the cost of this mistake. But on the other hand, let's say that, Pucci's predicted probability was like 25% or above, for instance, or any patient in general, hopefully not, touch wood. But if it's greater than or equal to 25% based on this probability threshold, and again, this varies based on the threshold, but if it is 25% or above, then basically what we do is then we're going to assign the patient to be predicted positive and go for treatment. And the true positive, this is sad though, but at least it's better than the false negative. At least in the true positive, when the patient actually is positive, instead of wrongly predicting they don't have the CHD, the model correctly predicted that a patient has coronary heart disease, and the threshold was reasonable, so the patient also was, predicted as being positive. So it's both the predicted probability from the machine learning model, that's what the machine learning model is responsible for, the predicted probability, and the probability threshold is based on us. We sort of react based on the predicted probability of the machine learning model. So that's what we are reacting to. This again is in the machine learning model, and then this is us or the doctors or other nurses or other people. But true positive basically is that overall we predicted patient is positive and should go for coronary heart disease treatment, and the patient actually is positive. So that was a win. And that was actually awesome because we made the detection, right? That people have the person who has that heart disease. But the actually negative, if the patient actually, if we predicted the patient has CHD and should go for treatment, maybe we wrongly predicted that. And maybe like, even if they had a 25% risk or 30% risk, there's still like, if they have a 30% predicted probability, there's still like a 70% chance they don't have coronary heart disease. But for this doctor with 25%, it's so much worse to have a false negative than a false positive. So the doctor said that, okay, well, I'd rather you wrongly go for CHD treatment, even if you don't have it, than risk you missing out on CHD treatment when you do have it. So the false positive, you're basically predicting a patient has coronary heart disease, but they're actually healthy. So this threshold, in other applications, it's typically 50%, 50% positive. If it's above 50%, you predict positive. If it's below 50% negative. But in healthcare, things are different and preferences are. And based on this threshold, we can see some things. And in this video, I kind of want to talk more about what this 25% means. But I hope you can kind of get an idea that this sort of weights the false negatives more than false positives. I have other videos on decision curve analysis, so please do subscribe to my playlist and my channel on YouTube and see decision curve analysis for more explanations on decision curve analysis. But I just wanted to tell you that for decision curve analysis for DCA, which is what it's commonly abbreviated as, typically select a threshold, and a positive is when predicted probability from your machine learning model for individuals or for rows or for anything that has a predicted probability of whatever it is, the disease, the condition. Here, it's the predicted probability that a patient has coronary heart disease. If that predicted probability is greater than or equal to the threshold, then you say that the person is positive for the condition. Otherwise, you say that they are negative for the condition. And when you're calculating clinical net benefit from a predictive model on the treated, in this case, then you take true positive count over the number of total samples in your data set minus the false positives over and multiplied by the probability threshold over 1 minus the probability threshold for a given probability threshold, and you keep varying it between 0 and 1. But in any case, so I have other videos just going over this and talking more about it. But what's key here is that this ratio, probability threshold over 1 minus probability threshold, is actually what is really key here. And that's sort of how the probability threshold sort of plays an impact in determining the clinical net benefit and sort of showing what your preferences are. So based on the probability threshold over 1 minus PT, it impacts not just the true positive and false positive counts based on the threshold, but also this is weighting factor that's really important. And it can help us also interpret the relative importance of both types of mistakes that are possible, of false positives, of falsely predicting a healthy patient does not have, a healthy patient who does not have coronary heart disease, predicting that instead that this patient has it. So falsely predicting that a healthy patient has a heart problem, has CHD, that's a false positive again, and a false negative is instead falsely predicting that a patient who actually does have heart problems, who has CHD, falsely predicting that they do not have it. So essentially, probability threshold over 1 minus probability threshold tells us false positives over false negatives, how you weight false positive mistakes to false negative mistakes. So let's say that a clinician chooses to treat a patient who has a predicted probability of CHD, coronary heart disease, that is 25% or above. That is that the clinician has a probability threshold of 0.25. So on the scale here of probability thresholds between 0% and 100%, this is the clinician's probability threshold, 25%. So this is where the clinician is at. And that's where the clinician's threshold is at 25%. So then based on this weighting, so a probability threshold over 1 minus probability threshold, so PT over 1 minus PT, then what we're going to see is that, it's 0.25 over 1 minus 0.25. From the equation I showed you, this is just the same as false positives over false negatives. That's how you can interpret it. So basically, the patient will be treated as long as he, she, they has a predicted probability of CHD that is 25% or above. So if you have at least a 25% chance of having coronary heart disease, then the clinician automatically assigns you to the positive class and predicts that you will have CHD and then decides to treat you. So then based on this, all you do is this is 0.25, this is 0.75, which is just the same as 1 over 3. 1 over 3 equals false positives over false negatives. So then from this equation here, you just multiply this side by 3. 3 times false positives equals 1 times false negative. So 3 false positives is equal to 1 false negative. So that's how you can kind of interpret it. For every 3 false positives that you make, it's the same as 1 false negative. So in the mind of the clinician believes that the consequences of a false negative, not treating a CHD patient, are 3 times worse than those from a false positive, so treating a healthy patient by thinking they have CHD. So this shows that the clinician really wants models with as few false negative errors as possible. Because if you think about it, with this being really low, already the typical prediction model usually assigns positive if you're above 50% and negative if you're below 50% as the threshold. So if you already are assigning, so basically based on this threshold, you're assigning everyone here as being positive. Anybody who has a predicted probability of 25% and up, you are assigning them to being positive. And then the rest you're just assigning to being negative below. And so basically, it's so much more common for you to assign people to the positive class where they will get treated for CHD. And because of that, what happens is that you are not weighting them equally. If they were 50% and 50%, like if the threshold is 50%, like it is for many prediction models, then what that means is that false negatives are the same as false positives. But here, and that's what typically prediction models do, they just assign 50% and up to positive, 50%, below 50% to negative, because false negatives and false positives typically are assumed to be equal. But the benefit, again, from decision curve analysis is that that may not always be the case. So you want to be able to just adjust your model based on your threshold, because you may not want to assign everyone to positive if it's 50% and above. You might want to have like 25% or 10% or maybe 80%, But because this is below 50%, you can kind of have a sense that false negatives are worse than false positives. So you really don't care if you're assigning them to the positive class that much, because since there's a greater chance of you assigning them to the positive class, there's a greater chance of false positives, and that's what you're willing to take. Here's like the false negative risk, but you're so willing to take that risk of having the false positives be higher because you're too scared of a false negative. You're too scared that somebody with a 25% chance of the CHD could still potentially, in your mind, be at a really high risk of CHD, and if we don't treat them, it can be worse, right? So that's where you are, that if they have such a high probability, like 25% might be high to the clinician or to the loved ones of the patient, so they might want to just get them treated. So that's how you interpret it. So usually if your threshold is below 50%, then a false positive is not as bad as a false negative in terms of errors. False positive is not as bad as a false negative. But if the threshold is above 50%, false negative is not as bad as a false positive. So when we said that a probability threshold of 25% essentially says that 1 false negative equals 3 false positives. So again, not all errors are created equal. When the threshold probability is 50%, then a false negative, 1 false negative equals 1 false positive. But here at the probability threshold of 25%, 1 false negative in the mind of the clinician is equal to 3 false positives. That is the utility to the clinician. So having 1 false negative is the same as 3 false positives, or probably even worse than having 3 false positives. So wrongly predicting that one unhealthy patient who truly has coronary heart disease is healthy, the mistake of making a false negative, of wrongly predicting that SpongeBob is healthy, that results in SpongeBob missing out on necessary treatment for coronary heart disease. This mistake is probably equal, if not worse, than the mistake of 3 false positives, of wrongly predicting that 3 different patients, 3 different healthy patients with healthy hearts, that they have coronary heart disease and sending them for unnecessary treatment. See here, the doctor is telling all of them, I'm afraid this doesn't look good. And all 3 of these patients are saying, please don't tell me I have CHD. Please don't tell me I have CHD. Please don't tell me I have CHD. They actually have healthy hearts, and now they'll be sent for unnecessary treatment. And at this probability threshold of 25%, the doctor is so scared of having a false negative. Essentially, in his, her, or their mind, this mistake here is equal, if not worse, than these 3 mistakes. The fact that this unhealthy heart is missing out on vital treatment is worse than 3 healthy patients going for CHD treatment. So you might agree with this, or you might disagree, and that's why this is subjective and why we have these probability thresholds in the first place. But this is how you can think about it. So again, this is just for the probability threshold of 25%, where we just showed that 1 false negative equals 3 false positives, or even is worse than that. But the results can change for different probability thresholds. It's like a moral calculation, a moral calculus, a utility, and it's based on the fact that, at 25%, then you're saying that, if you have like 4 different outcomes, and if there's even a 1 in 4 chance of having the disease, something greater than that, then you want to risk everything in a way. And it's like the idea that even if you have a 1 in 4 chance, at least a 1 in 4 chance in that situation of having it, you still want to go for treatment. So it's like the other outcomes are like the false positives, and this is a false negative, and 1 false negative is equal to 3 false positives in the calculation, because 25% is 1 out of 4. So this false negative, the mistake, the weight of this mistake, the burden, the impact is equal, if not worse, to the impact of these 3 people going through unnecessary treatment, these 3 false positives. And this would change based on the probability threshold, based on that calculation that we are doing of probability threshold over 1 minus probability threshold. So I'm a huge Star Wars fan, and with that, I just want to wish that the only negative things in your life, should they just be test results for coronary heart disease and for other diseases for you and your loved one, may everything else be positive for you guys. May you guys do well. So I'll say it like Baby Yoda. May the only things in your life, the only negative things in your life, be the test results for CHD and other diseases. So thank you so much for watching, and please reach out if you have any questions. And as my good friend Aina says,
Please like and subscribe.
yep, to my channel. So please do that and please share. Thank you guys.